However, consider for this equality, okay? Because if for example if be a s variable function and alpha an scalar, this norm equal to this integral alpha f to the power of p d mu, and by this power, and this is equal to this absolute value to the power of p, this integral to the power of p d mu of x, and all of this by this power, and so that this is equal to this absolute value and this. By this power, and this is equal to this multiplication, okay? Because in the following we see that this is a norm on the space of all s measurable functions such that this is a real value or real number, okay? And p norm does not change if f change on a set of mu measure. We know that if f equal to g mu almost everywhere, then these two are equal, mu almost everywhere, and so these two integrals are equal, okay? It shows that this integral, let me write smaller than this, okay? This integral equal to this integral, so that these two norms are equal to the norm, the p norm of g, okay? So that if f and g differ only on a set with zero measure, the norm of f equal to the norm of g, okay? by using the essential supremum rather than the supremum in the definition of this norm, we arrange for the infinity norm instead of p norm to enjoy this same property. Okay, think of this norm as the smallest that you can make the supremum of this absolute value after modification on set of measure 0. Okay, in all of this we consider if f equal to g mu almost everywhere, we consider this to equal, okay, or equivalent. This norm and this norm are equal. Okay, dear students, do you have my voice? Mr. Ghassan, Mr. Muhammad, do you have my voice? Do you have my voice? Example, P norm for counting measure. Suppose mu is counting measure on natural number. If A equal to this sequence is a sequence in or field and P belong to this interval, then the P norm of A, P norm of this sequence equal to this, and infinity norm of A equal to the supremum. Please note that if we consider x equal to natural numbers, x equal to natural numbers, any f from x to f can be considered as an sequence. This sequence, okay? For example, we can say f of n, n from 1 to infinity, or fn, let me write by calculate. Okay, this sequence, or we can write by this sequence. Because our domain is natural numbers, and so we have f1, f2, f3 up to the n. So this is a function from x to f, or from n to f. And we know that in counting measure, the integral of a equal to this. Okay, mu equal to counting measure, so that the norm of f, for example, norm p norm equal to this. to the power of p, d mu, and mu is counting measure, so that this is equal to this summation. Fn to the power of p by this power. Okay, and also infinity norm equal to this suitable, because this is a of k or f of k. Okay, this is a special case of p norm and infinity norm. Now we can define generalization of L1, which was defined in the second to last bullet point of example 6.32. Definition: suppose X S mu is a measure space and P belongs to this interval. P can be considered infinity. The Lebesgue space LP, sometimes denoted by this, for emphasis on all of this object X S mu, is defined to be the set of S measurable function f from x to f such that this norm be finite. Okay, so that let X S mu be a measure space LP of mu or more completely LP of X S mu, okay, X S mu in this measure space equal to the set of all f from x to f such that f is S measurable and this norm is finite, and this is equal to the set of all f from x to f such that f is S measurable and this integral is finite, because if this norm is finite, this must be finite and vice versa. Okay, example LP, when U is counting measure on natural numbers plus, the set LP mu is often denoted by LP by this notation, little l, okay, pronounced little LP, little LP. Thus, if P belongs to this interval, then LP equal to the set of all sequence in F such that this summation be finite and L infinity is the set of all sequence in F such that this supremum is finite. I mentioned that the norm P of f is finite if and only if this integral is finite. And norm infinity and as in a special case in counting measure, if mu is the counting measure on natural numbers or z plus, the norm P of a sequence such as this is finite if and only if this summation is finite. This summation is finite, okay? This summation is finite. Okay. Now we have this proposition LP of mu is a vector space. Suppose X is mu is a major space and P is a positive real number, then we have these two statements. This norm to the power of P is less than or equal to the power of P multiplied by this, and we have this equality, that we see this equality for all f and g in LP and all alpha in F. Furthermore, with the usual operation of addition and scalar multiplication of function, LP is a vector space. Please note that if f and g belong to LP, we know that these two are finite, so that this norm must be finite, and so f plus c must be belong to this. And if this norm be finite, this norm must be finite, and so this function alpha f must be belong to LP. It is very important that this is our definition for LP, the set of all s measurable functions such that the norm P of f be finite. Okay? It is very trivial that if f and g are s measurable, f plus c is s measurable and alpha f is s measurable. And by these two inequality or equality, we see that if these two be finite, this must be finite. And so f plus c must be belong to LP of mu. So that these two are very important. And its proof is very easy. Suppose f and g belong to LP. If x belongs to x, then we have this equality by triangle inequality. Please note that f of x is an scalar number because f is a function from x to f, okay? F is a function from x to f. So that f of x is a scalar number, and also g of x is a scalar number, so that this absolute value is less than or equal these two absolute value, and this summation is less than or equal to multiplied by the maximum of these two, because this is less than or equal this maximum and this is less than or equal this maximum, so that the summation is less than or equal to multiplied by this maximum. And we have this power, so that is less than or equal 2 to the power of p multiplied by these 2, because this maximum equal to one of these, okay? This maximum equal to f of x or g of x. In each case, this maximum is less than or equal this, okay? Maximum to the power of p equal to f of x to the power of p or g of x to the power of p, and each of these is less than this summation, so that we have this inequality. And if we take integral in both sides of this inequality, the integral of this function is this norm to the power of p, and the integral of these two equal to these norms to the power of p. This inequality implies that if this norm is finite and this norm is finite, the norm of f plus c is finite, and so this must be belonging to LP. And LP is closed under addition. The proof of this is easy, and we see this, so that LP is a vector space. Now we define the dual of LP. Please note that what we call the dual exponent in the definition below is often called a conjugate exponent or the conjugate index. However, the terminology dual exponent conveys more meaning because of result 7.25 and 7.26 that we will see these two that we will see in the next session. This is the definition for any p in this interval 1 up to infinity. The dual exponent of p is denoted by p prime and is the element of this interval such that we have this equality 1 divided by p plus 1 divided by p prime equal to 1. Okay. Example, 1 prime equal to infinity, because if we consider p equal to 1, this is 1, and 1 divided by p prime must be equal to 0, so that 1 prime must be equal to infinity. And if we consider p equal to infinity, this equal to 0, so that 1 divided by p prime equal to 1, so that this p prime must be equal to 1. If p equal to 2, this p prime must be equal to 2. And if we consider 4 for this p, we see that y divided by p prime equal to 1 minus 1 divided by 4. Okay. If p belong to this interval, p is a real or infinity number, such that we have this equality. Okay. For example, if p equal to 4, we see that we have, sorry, let me write in English letter, p equal to 4, we have this equality, so that we have this, and this is 3 divided by 4, and so p prime equal to 4 divided by 3. Okay. And also other conjugates. P prime is called dual exponent or dual conjugate. Okay. We have Young inequality. Dear students, don't have any problem? You have my voice and you see the image. Mr. Ghassan, Mr. Muhammad, do you have my voice? Do you have my voice? Suppose P belongs to this interval, then we have this equality for all non-negative real numbers A and B. And its proof is easy. Fix a non-negative real numbers B and define this function f from 0 infinity to r by this function rules. F of a belongs to this interval, equal to this. Then we see that f prime of a equal to this. F prime equal, because our variable is a, the derivation of this is equal to p to the power of p minus 1, and derivation of this equal to 0 because our variation is a or a equal to this. And this interval f prime is positive, so that f is increasing. In this interval f prime is positive strictly, and so that f must be increasing. So that let me write this for you. F prime of a equal to 0 if and only if is equal to 0, if and only if a equal to b by this power, okay, by this power. And okay, okay. In this point, a equal to b to the power of this f prime equal to 0, f prime of a equal to 0 if a be less than this f prime is minus, and in this f prime is positive, so that f in this interval is decreasing and in this interval is increasing. Okay, f is decreasing on this interval and increasing on this interval. Thus f has a global minimum at this point, a tiny bit of arithmetic, so that shows that f of this equal to 0, because f of this point equal to a to the power of p divided by p and other objects. We can compute this, that is equal to 0. Thus f of a is greater or equal 0, because we have this as the minimum and f of this point equal to 0. Okay, so that all of this must be non-negative. Okay, and we prove this f of a is greater or equal 0, so that we prove this inequality. And after this we can prove Holder inequality, that is very, very important. Suppose x s mu is a major space, p belongs to this interval, and f and g from x to f are s measurable. Then we have this inequality. One norm of fh is less than or equal these two norms. Please note that one norm of f equal to this integral. Okay, because this power and this power equal to 1. Okay, so that L1 of mu equal to the set of all f s measurable f such that this integral be finite. Okay, or the set of all mu integrable function, mu integrable function, mu integrable function. Okay, and the proof of this is very easy by the Frobius-Young inequality. Please read the proof of Holder inequality. It's very easy. Okay, and then we have this proposition: if P is less than Q, mu of it is finite, then we have this inclusion. Suppose x s mu is a finite measure space. Okay, mu of x must be finite, and P is less than Q, then we have this inequality for all f in LQ, so that we have this inclusion, because if this is finite, this must be finite. Okay, if f belongs to LQ, f must be belong to LP, so that LQ is a subset of LP. If we prove this inequality for any finite real number, this must be finite. Okay, so that we prove this inclusion. And this proof is easy for any f in LQ. Let R equal to Q divided by P. Thus, R is greater than 1 because we assume that P is less than Q. P is less than Q. Okay? A short conclusion shows that okay, it is very easy to check because we know that we have this equality, so that if we consider r equal to this fraction, you see that we have this equality, so that is equal to 1 minus q divided by p to this, so that r prime equal to this, okay. Q divided by P. Okay, this must be P divided by Q because must be inverse, so that all of this must be changed. Okay. My P divided by Q. This is Q equal to Q minus P, so that our Q minus P. Okay. Now that inequality with P replaced by R and F replaced by this function, and this right constant function 1 in horizontal inequality. Consider this change, okay. P equal to R F by this constant function 1, and so R prime equal to this. We see that this diagram equals, because we consider this the norm of this, and R prime norm of 1 equal to this. But to 1 equal to mu of x, the inverse of, okay, equal to this. So that equal to P multiplied equal to Q, and the inverse equal to P divided, so that we have the inequality side of the equation p. So it by this and this. So we prove this shows that belong to F must, and in what we see that we understand that if belong to LP of you and P LQ of you, then F must be like G1 of you, because if these two, sorry, I write Q in many books, component of P denoted by Q, okay? In this book denoted by prime. P prime. P prime. Okay? Because if these two be finite, this must be finite, okay? So that FH or FG must be belong to L1. And this Holder inequality is very, very important. And you can see some example for LP spaces and this inclusion. If P is less than Q, we have this inclusion. Okay? In this case, we have this equality because mu or lambda of this interval equal to 1. Okay? So that this equal to 1 and all of this equal to 1. The norm, the P norm of P is less than or equal Q norm of F. Okay? Okay, we have this equality. Suppose X, S and mu is a measure space, P belongs to this interval and F belongs to LP. Then we have this equality, the known P of F equal to this supremum of this absolute value of this integral, that H belongs to L prime and P prime norm of H is less than or equal 1. Okay? If this norm equal to 0, then both sides of the equation is the conclusion. In the conclusion of this result equal to 0, because if this equal to 0, F must be equal to 0 almost everywhere, so that this must be equal to 0 almost everywhere. Please note that if the norm P of F equal to 0, then this integral equal to 0, then this function equal to 0 mu almost everywhere, and so f equal to 0 absolute value of itself, mu almost everywhere, and we can come back to this conclusion. Okay, so if we assume that this norm equal to 0, f must be 0, equal to 0 almost everywhere, and so that all of these must be 0, so that this supremum is equal to 0, and we have this equality. Thus we assume that this norm is non-zero. Then by Holder inequality we see that this integrals is less than or equal the integral of this absolute value, and this is Holder inequality. Okay, this is less than or equal p norm of f and p prime norm of h, but we assume that this equal to 1, so that this less than or equal this norm. Thus all of this is less than or equal this, so that this supremum must be less than or equal this norm. To prove the inequality in the other direction, because we prove one side of this supremum is less than or equal this by Holder inequality. Okay, now we can prove another side of this equality. To prove the inequality in the other direction, define h from x to f by this function rule. H of x equal to this. Set h of x equal to 0 when f of x equal to 0. Then this integral equal to the integral of f. Sorry, the norm of f, because if we consider f multiplied by h, we see that f multiplied by h equal to f to the power of p minus 1. Okay, p minus 1. And so let me write for you h of x, sorry, integral of fh, the integral of f h d mu equal to integral of f multiplied by this conjugate, and this is f of x absolute value f to the power of p minus 2 and this norm p norm by this power. Okay, d mu of x, but this is a constant, so that is equal to this constant by this power, and this integral let's see v mu of x. We can write this integral equal to sorry, this is conjugate and this is conjugate, I write this is conjugate, okay? So that this multiplication equal to absolute value of f. This is equal to absolute value to the power of p minus 1 v mu x, okay? Because f of x conjugate equal to this absolute value, okay? This absolute value, and this is equal to this node okay, and this integral f by this power sorry, by this power p minus 1 we have this one plus p prime, okay? so that equal to this so that we must have this equality, okay, this is equal to P prime plus P by this power.